I'd like to introduce you to a project of mine called MakerCAD. MakerCAD's history is rooted in 3D printing the Curta calculator. A lot of the work that I did on the Curta calculator was designed in CAD. The CAD-based software, or the CAD software that I used was cloud-based, and that was great. I loved the fact that I could move between computers. I could work on it wherever I was. But I did have an issue. Who owns the work? It's really the cloud that owns the work, the company that owns the cloud. And I actually ended up with my work being public before I was ready for it to be. So I started thinking about alternatives for that CAD software, and I asked myself, what do I want in CAD software? The first thing is I would like for the CAD software to have a native format that is easy to version control. A lot of CAD software produces binary files or text files that get completely changed when you modify a model. So it's not easily version controlled. So I want to be able to keep track of the history of the work that I've done. I also want to be able to create branches to have different versions or different features on my models. And I want to be able to collaborate with others, share it. I also wanted parametric CAD software so that the model can be altered easily through parameters. This way you don't have to necessarily change code as much as change the parameters for your code to be able to generate a different model or a different size or whatever. In addition, I wanted to be able to use sketches and constraint solving when creating my models. It's a workflow that I got used to with the CAD software that I didn't have when I was using other tools like OpenSCAD. And so I really wanted to be able to draw out a sketch, set constraints on it, have the computer solve those constraints. And it makes a lot of modeling things a lot easier. In addition, I wanted to be able to model relative to existing features. So if I created a box and I wanted to create a hole in that box, I could position that hole based on the existing box and its edges or corners or whatever. I also want to be able to export to step format. The step file format, it makes it easy to be able to alter that model later, even in a different CAD suite. And it also makes it easier for other people to take that and make changes to it. There are a lot of free tools that are available, and a lot of those tools hit a number of these points, but not all of them hit exactly what I wanted. And plus, I have a little bit of a penchant for working on grand projects, complicated and difficult projects. So I decided to make my own. Let's talk about the software stack that I'm using. So at the bottom of it all, I'm using OpenCascade. It's a free open source CAD kernel to do all the operations that CAD software would need to be able to do. On top of that, because that is written in C++ and I wanted to be able to write my library, my tool in Go. Go and C++ don't always work well together. I wrote a wrapper that would expose a more C-like interface to OpenCascade. And then from there, I wrote Go OCC wrapper over top of that to expose that interface to Go. I also built a two-dimensional constraint solver called Delineate. And then over top of all of that, we have MakerCAD. All right, so let's design a simple model, a vice block for a lock. So this is what it looks like. I want to be able to. This is like a mortise or deadbolt type of lock that you put in a door, and I want to be able to mount it on a block so that I can mount that block into a vise. And so this is a fairly simple model, but it goes over a lot of the functionality of MakerCAD. So first and foremost, we have a little bit of boilerplate essentially for using MakerCAD, and then we get into some dimensions, some constants that we're going to use for uh, our model. I instantiate an instance of MakerCAD, and then create a box or a cuboid using the width that I define. I'm making it squarish, so the width and height are the same, or width and depth, and then I make the height a bit shorter because I didn't need the height of it to be real tall. And then the true at the end there is telling it that I want this block to be centered on the sketch plane origin. So I am using the top plane there. From there, I grab the edges of this box and I save those off for later. I'm going to round those edges later. And from here, I need to cut a recess in the block for the lock itself to sit in. So I find the top plane, or I find all the faces on this block that are aligned with the top plane, and I sort it by Z. So I'm going to grab the topmost one and create my my feature using that. And from there, I take that plane and I flip the normal on it so that I'm cutting downwards instead. I'm creating my cylinder downwards instead of upwards. And so I create that cylinder using the diameter of the lock and remove that from the block. Next, I want to create a couple of bolt holes so that I have a way to connect the lock to this block. There are two of them, and I didn't want to duplicate code, so I created a function. It takes a location and the geometry of the block itself. So it will essentially just create a cylinder through the entire block and remove it based on the location provided. So next, I call that function using the x offset for how far over I need that bolt hole from center. And I do that again using a negative value so that we have those two bolt holes on a horizontal layout from each other. Next, I need to find the surface of that that lowered cylinder recess for the lock, because the lock has on the back of it a cam that would interact with a deadbolt. That cam extends further than the back of the lock, so I need to be able to cut a recess for that cam to sit in. So the first thing I do here is I find the plane or the surface that I want to cut into, and I do that by grabbing all the faces and then saying that I want the faces that are aligned with the top plane, and then filter that further by finding ones that are at the particular height that I'm looking for based on the depth I've cut before. Next, I create another plane based off of that surface's location. With the previous cylinder, I flipped the normal and cut into the block, but on this one, I'm showing a different method of doing essentially the same thing. I'm just changing the location of that plane so that I'm reducing the Z height position of it down into the block so that I can create my cylinder normally and upwards, and still cut into that block. So I do that, and I cut that into the existing block. Now, there are a couple of wings on the back of the lock that would interfere with that back surface. And so I'm going to cut recesses in there to accommodate those wings. But when I cut into that, it's a rounded surface because of the cylinder shape of the lock. And so I need to cut this channel such that it has those rounded walls on either side. And that's a little more complicated, so I'm going to use a sketch. I'm going to draw this out, and I'm going to reference that geometry and create those curves. So first, I create an inline structure, using it to define a couple of the parameters for the geometry, just to make it easier. And then I'm creating a sketch based off the surface we grabbed earlier. Now I'm going to create the geometry, the initial geometry. Some of this is guessing on the actual geometry. I don't need to be exact on this because the sketch will actually solve for the exact geometry. So I'm creating lines and arcs, and the lines start with a start point in X and Y, and then an end point in X and Y. An arc is a center point, X and Y, followed by a start, X and Y, and an end, X and Y point. Arcs are always created clockwise. So you define your start as, or rather, you define your end point as being clockwise from the start point. And then we make sure that all of these edges that we just created, these lines and arcs, are coincident to each other so that we have a closed profile. So I'm using coincident constraints to make sure that the constraint solver is considering these points as the same. And then I'm going to put some constraints on the arcs themselves. So we set the diameter because we know the lock diameter of the hole that we cut before. And then I'm going to the center point of the arc, and I'm setting a coincident constraint with the sketch origin, which is in the center of that block. Next, I set a couple of constraints to make sure that the lines, the upper and the lower lines, are horizontal. And then we define that the upper and lower line distances are a specific distance from the center of the sketch, which is in the center of that block. So at this point, we have defined everything that we know, and we can have the sketch solve for the things we don't know, the start and end points of the lines and arcs. And once we do that, we can create a face based off of the sketch. And we actually have two of those channels that we need, and they're mirrored off of the center of the lock. So I just mirror the face once I've created it, instead of creating two different sketches and defining all of that geometry separate. I can create it once and then just mirror it across the front plane. Finally, I'm going to take both of those faces and extrude them into and removing from the block that we have. You'll notice that one of those is extruding -2 and the other is +2. It's because the mirror will actually flip the normal on one of those faces. So now we have the basics for the block. This is actually functional for our purpose at this point, but let's make it a little bit nicer. First, I want to chamfer the edges of some of these so that we don't have sharp edges. So I'm going to grab the shape that we have, and then grab all the faces from that shape, and then grab all those edges from all of those faces. And then I will filter that list by checking to see that those edges are circles, and then I look specifically for the bolt holes with the diameter of those bolt holes or the radius of those bolt holes. And that gives me some of the edges that I want to chamfer, but I want to add some more. So I will actually append to that list and do another filter off of all of the edges from that shape. And that filter is going to grab two additional circles. One is for the edge of the lock recess itself, and one for the recess for the cam. And then I simply just call chamfer on the shape, providing the edges and the distance that I want it to chamfer. Finally, let's round off those edges on that block. So we give it the edges that we had kept from before, giving it the current shape of the block, and 3 is the radius that we want to fill it. And now that we have everything finished, let's export those to files, and that's it. So let's do a demo of this. I have the actual code for that here. Let's see. So the code is here, and so I have this running on Windows Subsystem for Linux, and I can simply do a go run on the project, and that produced these two files. One is an STL and one's a step. So the STL you can take and put it into a slicer for a 3D printer. The other one is a step file, which, if I refresh here, I can open this up. So this you could use in another CAD suite and make additional changes, or share it for somebody else to make changes. But there we have it. We have the two files that are exported from generating that model. Now, what will you make?